Can you check? Yeah. A constant hissing sound. Yeah.
Yeah, there's constant like hammering.
Yeah.
I guess it was on. No.
Is that better?
No, somebody else's maybe.
It's totally quiet over here. Yeah.
I think that was Milap your side.
I think it's from me. I'll mute myself.
Okay, cool. Is that, we're good? Okay, awesome. So thanks a lot for taking the time to listen to this talk. So today I'm going to talk a little bit about doing Golang tracing and logging, especially with eBPF. And before we get into what that means, a little bit of quick background about myself. I'm Zain. I'm the co-founder and CEO of Pixie Labs, and I also teach at Stanford. That's my Twitter handle over there. Cool. So the problem that we're interested in tackling is, you're an application developer and you have a program that's misbehaving, right? So what do you typically do? In most cases, you go and take a look at the logs and see what's going on. And hopefully you have the right logs in the right place, and you will find out what the problem is and then go fix the issue. Unfortunately, as most of us probably know, that's not usually how it works out, right? Usually the problems that you run into, you don't really have logs and things you're interested in. And you're kind of like left with this question of like, what if I could just see what this variable was when a particular function gets called? So typically what you do when you're in development is you either go stick another log statement, recompile and run the program, or you use something like a debugger. So if you're in Go, and probably a lot of you already know this, is that you typically use something like Delve. And Delve is one of the main Go debuggers, and you can use something else like GDB as well, but that has less support for the Go runtime. So just to walk through some of the stuff, typically, you can just go get Delve, and we'll kind of walk through like a scenario to see how Delve would work, and then we'll talk about how we might be able to reproduce this experience in a different environment. So the first thing we did over here is have this like little demo application. It's a really, really small and silly app that basically has this function called compute E that computes like the natural, the exponential for the natural log. And it takes this argument called iterations because it's an iterative function, right? And it gets more accurate based on the number of iterations you pass it. There's a GitHub link to this little application, but basically this function is wrapped with an HTTP handler. So when you hit like the /e endpoint, it'll basically run this function for the specified number of iterations. Cool. So at any point during the talk, please feel free to stop and ask me questions. Happy to take questions anytime. Okay. So if we go back to this thing over here, how do we actually understand what's happening and be able to trace, for example, how many iterations this function got called with? So what you typically do is if you have a debugger, you will do something like delve exec the app. And then you can set a breakpoint, which is done by using the B command. And I have the nodes on line 15. So I set a breakpoint over there and start the server. So when I run something that accesses this HTTP endpoint, you will basically hit the breakpoint, and then you can print out the iterations and the values and all of it. So far so good. Debuggers are awesome because you don't have to go through this like recompile, rerun cycle. Cool. So what happens next? So the other cool things about debuggers is that they're really good at giving you context. One of the things you can do is you can type in this command called BT, which stands for backtrace. And that'll actually tell you like what were the sequence of events, or rather function calls, that actually led to this particular function being called with the argument that you're interested in. And another aspect that they can give you is something called Go routines, right, which is basically all the lightweight threads that Go runs. There are many, many other things that debuggers can do, and this is just like a sample of the functionality that you typically get. Cool. So debuggers are great. What are the pros and cons of the situation? So the first great thing about debuggers is that they provide you an easy way to get information without about the code that's actually executed. There's no need to like go add like a print statement and recompile, and you can easily step through the code to get the information you're interested in. Delve and GDB can also connect to remote binaries, so you don't have to physically be running the binary on your local machine to run a debugger. Unfortunately, this turns out to be a little bit harder in environments like Kubernetes, but there are some great projects like Solo and et cetera that make this process more manageable. So debuggers are great. What's the problems with running a debugger? So one of the issues is that you can attach a debugger to a production binary, but typically it's not a great idea to run a debugger on production binaries. Like in desperate times, like people have done stuff like this, but for the most part, debuggers can like mutate, stop the execution state of the code, and then that can actually lead to like unexpected failures. In a lot of production code, there's like a lot of parallel things happening. You interrupt the program, you might cause a bunch of different timeouts, and then crash your application. So the question is, if we really want to understand what's happening in production code, what can we do other than go to the old process of stick a print statement in, recompile. Now, since it's on prod, you probably have to redeploy it. Redeploying the code can, depending on where you work, could either take a few hours or, potentially a couple of weeks. So going through that long iterative cycle to debug something is typically very difficult to do. So at this point, you got to talk about what are your options, right? Well, option one is exactly what I said. Just go stick a log in there, recompile, redeploy, and deal with the pain that's associated with it. Option number two is, well, just go ahead and use a debugger and hope that nothing bad happens, right? And you can try actually writing some scripts around the debugger to make this process a little bit safer. There are a bunch of other like tracing utilities that Linux provides, and they have their own sets of pros and cons, which I'm not going to dig into right now. But there's another option, which is using eBPF, which is the title of the talk. So we'll talk a little bit about how you build something using eBPF. Any questions so far on this stuff? Okay, awesome. So with that in mind, let's dive into what is eBPF. Here's this very complicated chart that kind of explains what eBPF is. But I'll try to make this a little bit simple. If you're not familiar with eBPF, eBPF is basically a sandbox environment that runs inside of the Linux kernel. And the way that the kernel guarantees the sandbox is that you basically start off with some restricted C program. You compile it into a BPF target. I have no idea if you can see my mouse cursor, but I'm pointing to the development side where it says client target BPF. After that, it produces this thing called BPF bytecode, and this BPF bytecode can then get inserted into the Linux kernel. So there are a few things that happen, right? It seems a little unsafe to insert some code into the Linux kernel. Well, what typically happens over here is that when it hits the Linux kernel, it goes through this verifier process, and the verifier actually makes sure that, one, you cannot mess with the Linux kernel state because you don't want to break the machine. And the second thing it does is it makes sure that you're doing things that you're allowed to do. And after the code has been verified to not do anything disruptive, it also verifies that the code will terminate in some reasonable period of time. Basically, there's a maximum number of instructions that can get executed before the program will no longer verify. So essentially, it satisfies the criteria of this will not mess up your program or your kernel, and it's guaranteed to exit. And after it's been verified, basically there's a JIT compiler that runs. And in that JIT compiler, what basically happens is you take this BPF bytecode and then convert it to essentially like the machine code, executable machine code. And this property actually allows the BPF code to basically execute as fast as the machine will allow you to. So there are a bunch of capabilities that BPF has, right? And it's used for a lot of different use cases in networking, for building things like firewalls. But there's like a very specific functionality that we'll talk about today, which is something called uprobes. And what uprobes allow you to do in BPF, it stands for user space probes. And they basically allow you to essentially add areas in your user space program that you can analyze using these special functions called uprobes. We'll talk about that in a little bit of detail next. So before we do that, let's take our step back a little bit and see what do we want to build and how are we going to get there. So we already have this thing called, the app that I showed you a little bit earlier. It's a simple, really dumb HTTP app that computes the value of E. We want to write the uprobe function based on what I talked about. We will take the output of the uprobe and write it to this thing called perf buffer, which think about it as just as like a little queue that you write the data to. And then we're going to build another binary, which we'll call tracer. And the job of this binary is to read the data in the perf buffer and print it out. The actual process, what happens under the hood is a lot more complicated than this, but it's just like a high level, simplified view of the entire process, right? So take the app, have a probe function writes to a buffer, another binary called tracer reads the buffer, and we'll print out the value. And this is the goal of what we're going to build together. So with that in mind, how do we actually build something like this? So every binary encodes what symbols are available. This is true as long as the binary has not been stripped of all the symbols. It'll work for optimized or debugged binaries as long as the symbols haven't been stripped out. So if the symbols are available, you can use something called obj dump, which is an object dump, tell it to dump out the symbols in the binary. And remember that function earlier called compute E? We can basically just grep for it. And what we find out over here is what address is this function located at, right? And we know that there is a function called main.compute.e, and it's located in the text section. Text section is usually where all the code is located, and this is the address at which the code is located. So jumping back over here to the next call, I just use obj dump -d, and -d basically says disassemble the program and show me the assembly. And essentially search down for main.compute.e. And we notice this line of code over here where it basically looks at an offset from the stack pointer and writes it to the RAX register. So it's not super important to understand the details of this for the purposes of what we're building today, but Go passes arguments on the stack, and we basically are going to capture that value. Right, so remember we have compute E, it takes an argument called iterations, and that's located on the stack that we're going to copy into the register. Okay, so what are we going to try to do right now? So what we're going to try to do right now is we will take our application binary, use BPF or eBPF rather, and essentially add something called a uprobe hook, which if you're familiar with the details of this, it actually inserts like a little interrupt, which whenever it reaches this point in the code, it'll jump to the BPF program, and then our BPF program will then write the output to a buffer, and then our binary will read the output from that buffer and print it out. So essentially, we'll ask the kernel to safely mutate the binary, right, in memory, and then basically add a hook to our custom program that will read the arguments. Cool. All right. So this entire process seems pretty complicated, but it's actually pretty digestible, right? So what does this BPF program look like? So this is a function that will get called every single time. If we step back over here, every single time this uprobe hook gets executed, which is essentially when we reach this instruction on the application binary. Cool. So we write this function, and we basically register it by using these things called uprobes again. And one of the things is it'll basically run on every version of the binary. So if you're running like 2 copies of this, you'll see the output from both of them. So on the right side, you see the code over here. Let's quickly walk through it. It's really short. So there's a function says, there's a function called compute E called. This is a completely arbitrary name that I gave the function, so it has nothing to do with how the kernel determines what to use. And then it takes in this struct over here called ptregs, which is the pointer to basically a pointer to the registers, which is usually called CTX for context. So the first thing we did over here is read the EAX value. Remember, that's where we'll find the first argument. And then we basically do a perf submit. We declared on top a perf output called trace. And then we do a perf submit on the context, and then we write the value with the size of the value. Right? So essentially, when this function is called, we'll read the first argument of the actual function that's calling us, and then we will submit it to the perf buffer. I actually linked the GitHub to the complete example over here. There's a bunch of boilerplate, right, to go set up the probe and then read the buffer and print it out. It's all pretty straightforward, but it's just like a bunch of code that I didn't want to put on a slide. Okay, with that in mind, I'm going to jump into a demo, but before I do, are there any questions so far? Okay, awesome. Let me pull up the demo. All right. Can you see my screen still? Got free terminal view. Okay, awesome. So as you will notice, I am presenting from my Mac, but I'm logged into a Linux machine because BPF only works on Linux. So what I'm going to do is, just for reference, I'll actually open this up. Here's app.go, and here's our infamous compute e function, which takes iterations and runs for some number of loops. And then, as I said, there's just a simple HTTP handler that basically. Yep.
Hey, Zain, there's a comment in the thread says, question is, where is the perf buffer stored? And the second point is, can you zoom into your terminal a bit?
Okay. Is this good enough? I can't tell when it is big enough on the other side. Does this work?
Milan, does this work?
Yeah, it's good.
Okay, cool.
Yeah, so the perf buffer is basically essentially a shared memory region that the kernel allocates. So as I was mentioning earlier, there's basically an HTTP handle func that responds to /e, reads the number of iterations as iters, and then basically calls the function and then writes it out, right? So it's pretty straightforward. So the first thing I'm going to do is I'm just going to run the app function. And just to prove that it works, we will run curl on it. And I'll run it with iters equals 1. And you'll notice that it says the value of e, which obviously is wrong. Run it with iters equals 100, and you'll see it's a much closer approximation to e. And all this is pretty straightforward and works, and it's basically accessing this application. Okay. So then I'm going to dive into the next part, which is the actual tracer binary. So this is a separate program that's going to try to figure out what the argument values are for the compute e function. So with that in mind, here is the BPF program that you saw in the slides, right? It's reading the argument and then writing it to the perf buffer. And then, as I mentioned, there's a bunch of boilerplate that says here is a new loading uprobe or uprobe called compute e called, and then attach a uprobe to main.compute e, which is what the symbol is typically called, and then create this trace table, create a perf map, and then just loop through it and print it out, right? You can go ahead and look at the link on GitHub if you want to read through the program, but it's commented and pretty easy to follow. It's mostly boilerplate. So what I'll do over here is I will run the binary I will run trace and then specify the binary that I want to insert, right? And it needs to be run as root because BPF requires root access. So I will sudo that. And here, if we run this, we should see, look, we pass in iters equals 100, and it says the value equals 100. So we actually are tracing the arguments in this application, right, through another binary without actually modifying our original code. I'll do 10, you'll see it's 10. And if you want to see what the default value is, you can run it, and then the default value turns out to be 100. So all this works pretty autonomously. Yeah, any questions on this before I jump back to the slides? Okay, great. I think there's just a couple of our slides left, but basically, so what's next? So one of the cool things about this is that we realized we can use something like trace points for dynamic logging and allow you to easily instrument code, especially in production. One of the nice things about BPF is since it basically guarantees that the probe function exits in some reasonable period of time, you can easily run the function in a safe manner, collect the data, and then let the program keep executing. So it's all great, right? But the big problem is that the complexity of the Go ABI. The ABI is the application binary interface, and it talks about how variables are passed, like how arguments are passed to functions, where the return values are located, and how different things are encoded. Just the sheer complexity in the Go ABI actually makes some of this stuff really hard to do, especially when you consider there are things like interfaces and channels, right? I showed like a pretty simple example, and you can see how it's pretty easy to do for like a primitive type. It's pretty difficult to do if you want to do this on like a more generic basis, but it can be done. So anyways, it's a fun thing to play around with if you have some time. One of the things, as I get into the shameless plug, one of the things we are working on at Pixie is actually trying to make this process a lot easier. So if you're interested, please check out our stuff. And we basically are working on allowing you to essentially insert like a print statement anywhere in the code without actually modifying it. So you can take like a production binary, insert it in the code, and see what's going on. And there's some other related projects. Well, there's us Pixie in here, but there's also like the folks at Kinlope. They're doing some really cool stuff in Inspector Gadget, and then Sysdig also has some really cool stuff around monitoring, all using eBPF. So please check those things out. And yeah, thanks a lot for taking the time to listen. And I'm happy to take questions.
Thank you, Zain and Ishan. So, any questions?
Yeah, Zain, me again. So yeah, can we go back to the demo once again? Like, it was a little bit fast for me.
Okay, yes, I'm happy to go back to the demo. Sorry, now I need to find the share button again. Where is the share button? There it is.
Maybe if you go through one iteration of the demo, if you pass the argument slower.
Yeah, that would be helpful.
Cool. Which part of the demo did you want me to dive into on?
Yeah, pretty much everything. Sorry for that, but yeah,
like,
just slow it down. Like, I don't know if anybody had the same issue, but yeah, you are running the main application on your right top, right? And you are debugging at the bottom. So yeah, in meanwhile, like you pass the code and that tracing code, right?
Yep.
So how did that play along? Like just like one more time, if you could do that.
Yeah. I'll walk through it again. I'll try to go a little slower. So, and then feel free to stop me and ask me if there are any questions. So the first step is, excuse me. So here's like the application, and it's being served on like port 9090. The application has a single HTTP endpoint that basically we can curl over here. So I'm hitting localhost 9090 and then E, which is the single HTTP endpoint. Every time we hit it, it'll basically return as what the value of E is. It takes in like a single key called iters, which specifies like how many iterations to compute E for. The more iterations you compute it, the more accurate it is. The fewer iterations, the less accurate, but the faster it runs. So if you're running with 2, you'll see that the value is way off. So this thing over here is, you can imagine this is just like any HTTP server, right? It just has this small little function that you can access. Any questions on that?
Yeah, I think I'm good till that.
Okay, awesome. So the next step over here is that we have our trace binary, which if I go random stuff up, trace example, trace.go. Let me actually do this. Oops. Sorry. I think I messed with my terminal. Okay. So let me just open this up in like a bigger editor. Sorry, let me open it up on my machine. All right, this is probably a little bit easier to see. So this is the tracing binary that you saw earlier, right? And here is the BPF program. And remember, the BPF program actually gets compiled using Clang, and it's not part of the Go compilation, so we actually send it in as a string. This is that BPF program you saw earlier. So this is a C, like a restricted C program. It has compute E called. It has an argument, which basically is the context, which mostly contains a pointer to like the CPU registers, right? Even though it's actually a pointer to where the CPU register values will be located. And then we can read those values, and it turns out the first argument will be located here, and this argument should be iters, or the iterations, and then we will write that to the perf buffer. Okay, so this is what the upro function does. And what happens is basically every time compute E gets called, right when the function gets called, the kernel will switch over and execute this function for you. And then we can then read the values and then write it to the buffer.
So yeah, just like, correct me if I'm wrong. So you said when the program is executed, there would be an interrupt that will invoke this eBPF function, right? And
that is absolutely correct, yeah. So what happens is the kernel actually inserts an int3 function, or int3 instruction, which is actually a software interrupt.
Mm-hmm.
So yeah, as soon as the function gets called, it'll hit an interrupt. The kernel will then be like, okay, what am I supposed to do for this interrupt? And then it'll go call this function for you, execute the code over here, and then jump back to executing the regular function.
Okay, so the binary is already executing, it's serving as a HTTP server, and when we run this program, this is a program that we use for debugging. So it will do that mutation of the binary. Or...
Yeah. Basically the kernel will still safely mutate the binary for you.
So yeah, this is a little bit complex for me. Like I'm new to these things, but I think you guys are building tools to make it simple, right?
Absolutely, yeah. This is I think in some ways it's complex for everybody, even people who are experts on this. Like, this is very simple, but because BPF is so strict in verifying the code, it can actually get pretty hairy to write very quickly. And it by no means is supposed to be simple. This talk is more meant to like introduce a technique, not necessarily say go build all of this stuff, because it can get pretty complex.
Okay, cool.
Zain, first it might be fun to show like the Pixie interface as well, in terms of how easy it is. There's a question here from, how does it log multi-threads?
Yeah, I saw the comment come up. So it works the same way it would do it for a single thread. Basically, it'll hit the software interrupt. It'll go call your uprobe. You will run the function, write it to the perf buffer, and then it'll show up on the other side. So really not much of a difference. So Milan, just to close the thread over here. So when we run the binary, we basically specify the application that we're interested in monitoring over here, right? So at this point, now that, apparently I can't type my own password. My computer, I swear. Wow. All right, I think I got it this time. So when I basically run this curl function, and now intercepts it, goes and writes the perf buffer, and then we read the value out. So that's the second part of your question for the demo.
Okay, just a tail question here, Jen. So when we run this trace program, how does it know, like based on the binary, it will mutate the code? Like it should know, right? Because the app is already running somewhere on the memory, and how does it like does this probing thing? Like, does it check some signature or?
So yeah, that's a great question. So the way that so this actually gets into like fundamentally how Linux thinks about executing and running code. When you launch a program in Linux, it typically maps it somewhere in memory, right? And essentially every binary is mapped to some location in memory when you execute it. And if you run 2 copies of the binary, it'll actually reuse the same code. So because you don't want to waste virtual memory space. So when you pass the app over here, it'll actually go and effectively modify the master copy in virtual memory. So every binary that's running app will have this, if that makes sense.
Okay.
I could have actually shown you this if I don't think the port is configurable, but if I made the port configurable, I could have started 2 copies of this, and then you'll be able to see both binaries print out their values.
Okay, yeah.
Because it actually instruments the binary, not a particular process. Like if you see over here, I didn't pass a process ID or anything. I just said instrument this binary.
So it will come it will just go to that memory address and just mute it. But could there be case like the real program could have like different signature compared to the like binary you are trying to trace? Could there be case like that?
Sure. I think there are probably cases where that can happen, especially in binaries that have like self-modifying code, right? Like other JITs and things like that. But those cases are not super common. I'm not 100% sure how UPerfs work in that situation. I suspect that they'll still work. They'll probably just have a little bit different behavior if you go and try to probe the JIT code. But in most cases, the binary should match.
Yeah, thanks then.
Yep.
It's much clear now. Like I think it's clear for others also.
Yeah, of course. Thanks for asking for the clarification. Cool. Was there another question?
Yeah, many more. Yeah, quite a few. Go for it. Pretty nice questions.
How does log multi-thread be used?
Yeah, after that one, can it be used for networking and other stuff other than logging?
So yeah, I can actually show some stuff that we do at Pixie, but we can even do stuff maybe used for other things like networking. Absolutely. Like for example, you could probe the to see like how long DNS resolutions take. There are other things that you can deploy, things like K-probes that actually stand for kernel probes, and they allow you to access like the syscall interface, right? So you'll be able to see like what different syscalls do or what different functions within the kernel do. So eBPF is pretty extendable. Okay, so the next question was, do we need to know the address of the variable in eBPF program to print it? Yes, I think the short answer is yes, you need to know the address somehow. There are a few different ways to get it. So for the variable, you don't really need to know the address because the variable is like located on the stack somewhere and the ABI documents it. But in order to find the function, you need to know the address. So we use the name to find the function, and that can be done if the symbols are present. You can just see what address the name corresponds to. And if you notice, let me switch back to the slide up here. If you notice, the first thing we did over here was we ran obj dump to find the address of interest, right? And effectively, under the hood, that's what's happening. If you don't have symbols, you will need to know what the address is. So the short answer is yes, but you can usually use the names to find it. So if you're using hooks in memory space, are there any security concerns? I think the answer to that is yes, there are potentially security concerns because you can go and add logs, but so can any debugger, right? So the security constraints are different than what you would have in a debugger. It's just something that usually has to be guarded by some system that manages the security. Cool. Next question is, can it be used for distributed tracing, something similar to open tracing? So distributed tracing is used to try to pass context around different machines. And this is typically used to try to understand what's happening within a single machine. Part of actually what we're working on at Pixie is taking some of this stuff, which allows you to monitor like machine level information, and then making it accessible across machines to try to solve the distributed tracing problem as well and make that process simpler. We look into logs. How can we look into logs to see which distributed that corresponds to which instance of the log? Okay, so if I understand this question correctly, you basically want to know that if some request gets called and there's like a particular Go routine ID or something, how do we get that information? It turns out you can probe some more data structures to figure out which thread is executing and what the Go routine IDs are and stuff like that. I didn't dive in the talk because it starts getting pretty hairy, but all those things are accessible. Any other questions? I'm happy to show like the stuff that we're working on at Pixie if that's useful. I can just quickly show how that works.
Yeah, we are interested to see like what you guys are building.
Okay, awesome. So I have Pixie pulled up over here. Let me go to my demo cluster. So part of what we're building at Pixie, sorry, my demo cluster is, okay. Part of what we're building at Pixie is a system to help you essentially understand applications on Kubernetes and the whole distributed system, right? So for example, I'm running the online boutique application, which right now is not showing anything, but let me go and access it. Show you what online boutique is. So. I need to get the external IP of this. All right. So here's this online boutique application. It's like a distributed services application that allows you to buy things, right? So it's like a typical e-commerce type program. You add to cart, place an order, buy things. And then you can say, keep browsing to go around. Okay, so if you go to Pixie, we basically will automatically discover like the topology of the application based on the requests that are happening and give you all the really high level information about what are different parts of the stack doing, what are their latencies. If you dive into a particular application, you'll be able to find out what the requests are and then a sample of like the slowest requests that the application is typically seeing, right? And by utilizing all of our eBPF stuff, we actually do like full body tracing. So I guess it turns out that this thing sent an access token and we captured like the entire body of the request. So that's what we do at Pixie. We can allow you to basically start at this pretty high level, kind of like navigate through your services, and then basically dive into like the details of a specific request. And all of this is like fundamentally driven by some Python script, and you can play around with it and modify it, and even contribute scripts to the Pixie repo if there are use cases you want to solve. So how does this play into a lot of the stuff I just showed you? Well, one of the things that we allow you to do is actually add dynamic instrumentation to the applications that are running. So for example, Online Boutique has this thing called checkout service. And one of the demo scenarios I can show you quickly is we can take a look at this file over here. which is in the online boutique repo, which is called Google's microservices demo. There's checkout service. Checkout service has this thing called money.go. And in money.go, there's this function called sum, which actually adds up, two different money values of different currencies. So it's a little bit more complicated than just adding numbers, right? Because it has to actually do the math. It does like fixed point math, which is what you're supposed to do for money. And it also takes the currencies into account. And it takes two values, which are the left and right value. And they're basically protobufs that consist of two fields called units or three fields, units, nanos, and currency code. And actually, one of the demos I'll show you is how we can easily add a probe to go find the values of this function. So with that in mind, I need to grab the ID of the checkout service and dive into, switch this to checkout trace. So what we can do over here is, this is like a little pre-baked script for this. It basically says go find money.sum and then print out the values for units, nanos, and return values. Eventually you'll have like an interface where you can just click on the code and get the results, right? But right now you have to type in the raw script. We can then deploy this probe. Usually takes a few seconds because we have to go modify the binaries and shift the data around. Great. So now it's running. We don't see any data, but that's because nothing's running on this cluster. So let me go try to buy another vintage camera lens. We'll place an order. And then, sorry, I see the wrong screen. I go where you hit run. Look, we trace the values of that function. So this is like a service that's running in production. And we were able to go pull out the values without actually ever stopping or modifying the service by hand. And here's a time, here's like the Go routine ID. So someone asked about how this would work with threads or distributed environments. So the Go routine ID is the ID of the Go routine that ran this, and then the actual protobufs. Cool, I'm looking for the questions. Can I know the health of a, sorry.
Oh, sorry. Yeah, go on.
Oh, go for it, Milan.
Okay, so yeah, this looks very much simplified. Yeah, obviously very much insightful. Can we try your application, like, and also like there's a tail question, like when you deploy that hook scripts, how does that like get deployed in the cluster?
Yeah, okay, absolutely. So first thing, can you try it? Absolutely. We have like basically a free community version that you can try out, and we have a community Slack channel. We'd love to get feedback on it in terms of how you're using it, what you're thinking about, and be super excited if some of you try it out and let us know. How does this deploy? So one of the things is Pixie does run on Kubernetes. So as long as you're on a Kubernetes cluster, there's like if you go to our docs page, there's basically one single command you can run, and it'll basically install Pixie. It just curls install.sh. And it'll basically install Pixie, and after it's installed, you can go play around with the Go binaries. And if you have any questions, feel free to reach out to us on Slack.
Okay, sure. Thank you.
Cool. So the next question was, can it look at things like health of the server, like if server goes down? So Anvesh, that was Anvesh's question. Can it know the health of the server? So yeah, there's actually some stuff with eBPF that'll allow you to find out if a program is crashed or why it crashed. We haven't put that into Pixie, but those are the types of things we're looking at and other people have looked at. Basically, the binary crashes, report something up. If the server's not running, report something up. How mature is the technology at this point? I heard that there's a limited number of instructions. So that's a question from Rabin. if I'm pronouncing that right. How mature is the technology? So Pixie is in beta. eBPF itself is actually used for a fair number of applications. It needs a relatively new kernel, but it is definitely a production capable thing. There is a limit to the number of instructions that BPF can execute. I believe it's like a pretty small number, like 4,000 instructions. But keep in mind that one, it's kind of for your own safety because you don't want to hang the Linux kernel by executing like millions of instructions. But in a newer, I can't remember the exact Linux kernel version, but in some newer Linux kernel, they bumped up the instruction limit. They can do slightly more complex things. Yanki Marajan asked, does this work on a single node that you define or is shared among all nodes in the cluster? So I think you're asking this one about Pixie, correct me if I'm wrong. But the answer for Pixie is yes, both scenarios are possible. We can allow you to instrument even a single binary or allow you to instrument multiple binaries across the cluster.
And if it's just the plain simple eBPF binary, then it is like node specific, right?
Yeah, so we actually figure out what node it's located on and do all of that stuff for you, so you don't have to think about it. Yeah.
I have one question as well. In case of AWS, like serverless lambdas, how does this, can we integrate it with lambdas? Like would that runs in Go binary?
Sadly, no, because I don't think Lambda exposes an eBPF interface. But my guess is like over the next couple of years, like eBPF is a pretty hot thing and it's getting used a lot. So there'll probably be some way to do this. It's just there's no way today.
But what if we are like running serverless on our own like Kubernetes cluster that is sharing our node resource? Yeah.
Yeah, then it'll work just fine.
Okay.
Cool. Any other questions?
I think that's all of the question.
Yeah, thanks a lot for taking the time. This is super fun.
Yeah, thank you for the talk. It was really insightful and helpful both for me, and I think it was same for the audience as well. Thank you for giving us the time. I think it's like a little late there, and it's a little early here in Nepal. So both of them for giving the time. So lastly, we have a JetBrains license to give. So we'll do just a raffle to give one to any one of you the license. So Yankee, would you like to do that?
Yeah, sure. So we have a JetBrains license for 1 year, I guess. So all of the people who registered by meetup.com would be eligible for this raffle. I think I'll start sharing my screen for that.
Meetup, we gotta drop off. All right.
Oh yeah, sure. Thank you. Thank you for joining and thank you for your time. Thank you, Jane.
Thanks.
Thank you, guys.
Thanks.
Thank you.
Thank you.
Okay. So Dinesh Kotwal, is he on this meetup right now? I think not. So I think we have to go for another one. RJ and Cherry. Do we have RJ and Cherry on the list? Nope. Krishna Chalise. Okay, we don't have him as well. Okay, Milan I cannot win, I guess. Neil Koirala. We don't have him as well. Okay. I think a lot of people have already left. So again, wow, lucky guy. MJT is not here. Remove. Okay. Rajiv Shah. I think we should just give it away to like someone who really needs it, I guess.
Yankee, you can include my name, and I'm sure I will be selected.
Okay. Sorry, like you didn't sign up through Meetup, so we can't do that, I guess. uh, okay.
I think it's okay. Like if anyone wants it,
Yeah,
then
like
please
if there
comment.
is a student here, I think it'll be best for a student or someone like that. JetBrain license. So okay, Izu Tamang wants it. Sankar Acharya, do we have him? Okay.
I want to pass. Like, I don't want it.
Okay. I guess we can like give it away to Yezu. Like, what do you think, Miladai?
Yeah, we can do. We can do that.
Yeah. Okay. Congratulations, Yezu. You just won yourself 1 year license for JetBrains product. So yeah.
As you please send me your email. You can send me in the meetup.com or any place where I can send you the license.
Yeah, so I guess that's all for today's event. And by the way, we also have a new organization on GitHub, Golang Nepal. So if you want to like add new cool projects or work on an existing one, I guess there's just a single one, our Go Nepal site. So if you want to contribute on that as well, so we have that. Uh, so yeah, apart from that, I hope this was a great meetup. Milabda, do you want to add something?
It's. I think Susan Mananda is asking if it's open source. Yeah, it's open source. And like we are also planning for next meetup in October, and we already have one speaker for that. And we also want one more speaker from Nepal to talk on that. So if you are interested to talk, it could be it could be beginner level talk or advanced, anything will be fine. So you can just contact us via meetup.com or Twitter or anywhere. Yeah, that's it
Yeah,
from me.
we just want to keep the community active. Yeah. So yeah, also I want to give a shout out. Tomorrow we have a DevOps Nepal meetup. I think CNCF kickoff Kathmandu. So like Rajuda is here as well. So I think he can give the context on what tomorrow's event is about. So Rajudai, you can take over.
Yeah, thank you. So yeah, we are having a kickoff meetup for the CNCF Kathmandu chapter at 9 p.m. Nepal time. Maybe late, but but let's expect for we are planned for like 1 hour. Let's see how it goes, and it will be mostly Q&A session with Kelsey. So we'll like send a form or something for collecting the questions also by late today, I think. And yeah, it will be more interesting, and let's keep the energy going.
Yeah, I think it's a great feat for the community that we have finally joined the CNCF community. I was really excited when you posted the news. Yeah.
Yeah, exciting thing happening in Kathmandu for developer community and anything. So yeah, let's collaborate more and bring
Yeah.
bring all the community together.
Right. Right.
Yeah,
So
yeah, I think we
I
can
guess
wrap this up now.
hmm. So yeah, Thank you everyone for joining in. So if you have any ideas, like Milab Dai said, you can reach out to us. And we have our meetup community pretty active, and we are open to suggestions. So yeah, I think that's all. Also, like we are also looking for contributors. If you have like cool project ideas, just hop into the organization and create projects there. Yeah, Zain, Milab Dai.
Yeah. Thank you, everyone. Thank you for joining us. Bye bye.
Yeah, okay, bye bye.
Thank you, guys.
See you in the next meetup.